Okay, Mr. Hunt here. I'm going to go through the circles practice test. I'm going to jump in and really just go question to question. Pause the video if you want to stop and think about one. Really make sure you've tried these as well first, too. So try them first, see what you know, what you can do, and check them over here. Okay, number one. NJL. NJL is a semicircle, so it's going to be 180 degrees. Measure of the arc. M means measure. NKM. Let's see, NKM around there. Now they gave us LK 70 and then NM. And here's 75. So I can just do 360 minus the 75. Things up there, we do know it's circle D. So we do know semicircles. We know 360 is the full circle. Just things you can use. Also, NL is 18, so that's going to help us that the radii are all 9. Circumference 2 pi r, and the radius there is 9. Now it says leave your answer in terms of pi for 6, C, D, E, and F, C to F. So that's 18 pi. Now arc length. So I put these in order because watch how similar these are. The only difference here, now be careful, not arc measure, arc length. It's part C, but the only difference is you have a part, a measure of an arc here, times 2 pi 9. So notice you're still going to get 18 pi, but you're going to do a part of it, a fraction of it. So what goes there? We need the measure of arc K and N. K to M to N. And they gave us that LK here of 70. So we can do 180 plus 70 to get that this is 250. Again, do not put for this one the answer as 250. That is the measure of arc K and N. We need the arc length, which is different. It's a part of the circumference. So you put these in your calculator, 250 divided by 360 times 2 times 9. You get 12.5 pi. Again, leaving pi out. Or you could, 25 halves would be the fraction. Area of the circle, pi times 9 squared. So you get 81 pi. And then area of the sector, it's just like E, but so we'll have part of the circle. So I need something over 360, and we're with NDK. Oh, it's the area of that sector. Now, I would have to shade this. Let's go red here. It's supposed to be the smaller one, because it's kind of unclear if I meant the smaller or the big one. So based on a minor arc of NK. So it's the shaded area there. So this arc is going to be 110. Since this is 70 and we have a semicircle, I can subtract from 180, 180 minus the 70. 180 minus the 70, you get 110. So in your calculator, 110 divided by 360 times 9 squared. Leave it in terms of pi, so you get 24.75 pi. Okay, moving on. Number 2. There was a theorem. The construction for a center of a circle is take a chord and perpendicular bisect it, right? So if you have a perpendicular bisector or a segment coming from the center, it would bisect. Well, these are not. If these were both 10, that would help us out. We know that. We know it would be perpendicular, but it's not. So we can't use that theorem here. So we're going to resort to the random segment in a circle, that theorem. In other words, the A times B equals C times D theorem. This I always say multiply the parts based on a proportion because of similar triangles. So anyway, 8 times 10. That's the parts here. The parts here are x times, and we'll put it in blue. That segment there is what I need. Well, they give us that 12 for a reason. That's the radius. And what we can do is I can say this hole in purple here is 24. That's a diameter. So basically, here's my setup. I know this is x, and this is 24. And I would like, in blue, that segment. because then I can finish my formula over here. Well, segment addition, x plus something is 24. And therefore, 24 take away x will give us this. So 24 minus x represents the blue. And that goes there. Okay, distribute. Here it's 80. Here we distribute 24x minus x squared. Get an x squared, x term in a number, so I'm going to have to factor, attempt to factor. I'm going to have everything on the left side. So I'm adding x squared, subtracting 24x, and keeping the 80 equals 0. You factor trinomial, and it will work. You'll get minus 4 and minus 20. Those multiply, you get 80, add, and get negative 24. So we get 4 and 20. Now we always need to look at those. Normally negatives don't work. Here we actually get another one that doesn't work. The 20, I'm throwing that one out. Keeping the 4, but the 20 doesn't work because if 20 is this part, all right, that's just part of the radius. Well, the radius is 12. So I can have a part of the radius be bigger than the radius itself. So I'm throwing out 20. 4 works. 3, circumference formula is 2 pi r or pi d. And we're going to fill in the 32 as the circumference. Now, it's not 32 pi. There's no pi that cancels here, which is fine. But we can just divide by 2 pi. Making sure to divide in your calculator by parentheses 2 pi. Or if you had alpha f1, then it will be fine. So don't do this because your calculator does 32 divided by 2 times pi. So you got to either use parentheses here, and then it will work. Right? Or alpha y equals, get alpha f1, hit enter, and then you can put it in here, and it will work fine. Okay. You double it to get the diameter, so radius was, I'm putting about, it's rounded, about 5.1, 5.09. Double it, about 10.18 or 10.2 for the diameter. One other note, the only thing that's on the formula sheet is the circumference formula and area formula. This one here. But you could also use circumference as pi d. And so you could have taken 32 and divided by pi. That would work as well. Moving along, this is the party hat theorem one. Q is an exterior point. I would have to mention in there too something about tangent. So 2 tangents from an exterior, I should say, segments that appear tangent are tangent. I would make sure to put that in there. So QT and QU appear tangent, they're congruent. They're from the same exterior point. So they're both 12.5. UR and SR is 33.6. Well, R is an exterior point, and those are both tangent. And same over here with PT and PS. Exterior point P, so they're both congruent. I'm writing in, by the way, they give us some of these numbers over here. Okay, so we add them up. And you get 131.6. So find the perimeter of the triangle. Last one on this page, circle as so we're working backwards here. Circle has an arc length. And here's the formula. Measure of the arc over 360 times 2 pi r. Now above, in one part of number 1, I actually fill in everything on the right, just evaluate. This one says put in 3 pi here for arc length. We're finding the measure of the arc. You can leave it like that, I like to call it x. And then put in 6 for the radius. And so we can actually work backwards. First thing I like to do on these is cancel a pi. I'm really dividing both sides by pi. It cancels. If there was a plus or minus in here, somewhere it wouldn't work. We divide every term. So here there's really one term on the left, one term on the right. Dividing both terms, both sides by pi. Then I'm going to clear the denominator. Multiply both sides by 360. Let's see. So we'll get 1080 on the left side. X and then 2 times 6. So that's 12x left on the right. divide by 12, and we're going to get 90 degrees. That's the measure of the central arc. Okay, so that would be like, we found the measure of the central arc, also the measure, I'm sorry, central angle, also the measure of the arc. Okay, flip it over to page 2. Here's good to convert degrees to radians. So 72 degrees. You just got to remember the conversion. You can remember it like this when we talk about radians. Halfway around the circle. Right, this was 1 radian, 2, 3.14159. Halfway around, so 180 degrees, is equivalent to pi radians. That's the conversion right here. So what I'm doing is I need degrees to cancel on. So I'm saying if you forget the conversion rule. Degrees on bottom, so I need 180 degrees here and pi radians here. Again, if you forget, you can rely on this. The rule is just times pi over 180. So degrees cancel. I say leave your answer in terms of pi. Now, I say times. It is. It's times a fraction. But there's really 72 over 1. So 72 is really in the numerator. 1 times 180 is in the denominator. It really becomes a division. It becomes a fraction. So it's 72 over 180. I prefer reduced 2/5 or 0.4 to say that. Let's do this one. I want to say one more thing about radians. It's the reciprocal here to convert radians to degrees. So actually, so that's 4/9 pi radians. So we're going to multiply by 180 over pi this time, the reciprocal from before. And this is degrees, and this is radians. The pi's cancel, the radians units cancel. And so now we just do 4/9 times 180. And we get 80 degrees. Okay, one last thought about radians. What is a radian? Take the radius, take that exact length and put it along the arc. Connect the arc back to the center. Make your angle. That's 1 radian. If you take exactly 3.14159, etc., you would get halfway around the circle, and that's pi. It's very cool. Moving on to 7. There's, again, this is one I should have stated, I'm sorry. Assume segments that appear tangent are tangent. So here's a tangent, here's a radius, and so that's a right angle. Now what we can do is Pythagorean theorem. R squared plus 3 squared equals the hypotenuse, which is R plus 1 squared, not R times 1. The left side is just R squared plus 9. The right side is not R squared plus 1. You have to FOIL. So let me write it out. It's R plus 1, R plus 1. So here's where I FOIL. R times R is R squared. R times 1 is R. 1 times R is R. 1 times 1 is 1. Now let me go ahead and combine these terms. At the same time, I can cancel an R squared. I'm really subtracting R squared from both sides. So the left side is going to be left with 9. The right side is 2R plus 1. So we subtract 1, divide by 2, we get 4. Okay, moving along. A lot of good ones on 8. So most of them are pretty quick. So let's just go through them here. In A, so again, central, inscribed, other angle, random angle, I'll go through it. So identify what you have. I don't have any central angles, but B is an inscribed angle. So B is going to be half A. I can get A by subtracting these two from 360, so we'll get 98 left over. B is half that, so it's 49. B, no central angles, no inscribed angles. There's no angle with a vertex on the circle. I mean, if it was connected like that, maybe that one, there is none. 2 ways to do this one. I like to do it this way, where I know angle 5, that's what we're solving for, by the way. Didn't have an X or Y here, sorry. That's the variable. Angle 5 is a random angle on the inside. The measure of angle 5 will be half the sum of the two arcs I put up here. The two arcs that it intercepts. Its arc and then its vertical angle's arc. Well, I can subtract from 360 to get that the arcs in red sum to, quick subtraction, 244. I can fill that in here. This is the sum of the arcs. I don't need them individually. I just need the sum. So we get 122 degrees. Sometimes we have problems where we do know the individual ones, but this is just for the sum. Another way to do this one, I'll show very quickly, is do the normal formula to get, I'll call it x here. X is half the sum of 66 and 50. So when you do that, you would get 58. Then you could subtract from 180, because these two make a straight line, and you would get the 122. Move this over a little. For C, it's the parts one. There was like number 2 or something from the front page. I can multiply these parts. X times 12 and 6 times x plus 2. Make sure parentheses here. Because sometimes students will do this. 12x and they'll write 6x plus 2. They won't distribute. So you got to distribute this. It was 6 times all of x plus 2. Subtract 6x, and then divide by 6, so we get 2. This one is an angle outside, right there. Now, we're solving for x, which is part of the arc, but you got to identify, what do we have? I have an angle outside. That's the formula I need to start with. An angle outside, is half the difference of the two arcs. So that one, what is it, 30, is half the difference outside 90 minus inside 2x. Always outside minus inside. The outside one is also the bigger one. Inside will always be smaller. You can distribute the half. Feel free. 45 minus x, that would work out nicely. I like to just clear the denominator by multiplying both sides by 2. I get 60 equals 90 minus 2x. Quick solve, 15. Okay, in E, let's start with x. X is an angle outside. So it's going to be half the difference of the two arcs it intercepts. That arc and this arc. Then you guys say, all right, well, how can I find those two arcs? Well, the 18 and the 34 are there for a reason. The 18 is inscribed to this arc. Therefore, the 18 is half. So the arc we want, the inside one, is 36. Outside minus inside, so 36 minus second. Next one is the same idea. The y, this arc we need. It is inscribed for the 34 angle. So the angle's half. I can double 34 to get this as 68. I work that out. We get 16. And then, guys, y is a random angle on the inside. It's this angle right here. It's half the sum. Well, the sum of the two arcs. Well, let's see if I can outline it again here. The two arcs that it intercepts are this one and this one. That's the same two arcs from x. So it's still going to be 68 and 36, but it's half the sum this time. So we get 52. All right, at the bottom, let's see here. So F, I have segments outside a triangle, outside a circle. So I can do the whole segment times the outside. That's the kind of rule for this one. So the whole segment, let's start with the tangent one, is 6 times the part of that segment that's outside of the circle is also 6. Then I go to the secant segment. The whole segment is x plus 5, x and 5 together, times the outside part of that segment is x. So we get 36, and and we get x squared plus 5x. And guys, it's a factoring one. I suggest you try it on your own here. Not going to take a lot of time for this one. We get x plus 9 and x minus 4. And so therefore we get negative 9 and 4. But I'm only taking 4 because I can't have a segment be negative 9. Let's go to the next one. Notice I have 38. That is a central angle. There's a dot in the center. So that they're saying that angle is 38. Therefore, the arc, it subtends. The arc here is also 38. Central angles are the same as the arc. Okay, but then we want A. Well, A is inscribed for the 38. Okay, so A is going to be half that. It's 19. We can get C now. Notice that C with the 38 and this arc is a whole circle. So to get C, I'm subtracting 146 and 38 from 360. I get 176. B is not a pure inscribed angle, but we can use the inscribed angle theorem as long as there's one chord and one tangent. We can still use that theorem. So it's half of 176. So B is going to be 88. H is a simple one, but you have to know it. The inscribed quadrilateral in a circle. The opposite angles are supplementary. Okay, these two, or B and D are supplementary. So we subtract from 180 and we get 46. That's pretty simple, but gotta know how to do it. The opposite angles, inscribed quadrilateral, supplementary. So we subtract from 180. In I, it's the parts one. Just kind of give you another one of these. I guess, yeah, I'd be a little overboard here, but 6 times x and 4 times 12. So we get 48 and 6x, and then divide, so we get 8. Last one, we kind of already did it on part G with the 176. Notice that this is not a diameter. It really looks like it, but figures aren't always drawn to scale. And there's no center dot. So that is not a diameter. But we can get x as being half. It's chord and tangent. So we can use the inscribed angle theorem. Half of the 182. So we get 91. You can see, I mean, it was close to being in a center diameter, because if it was a center, it would have been a right angle being a tangent being x 90. It's 91. Subtract 360 from 180. Subtract 182 from 360 to get y, because it's the rest of the circle. We get 178. All right, let's move on to page 3. Area of the shaded region over there. I'm going to do the area of the sector and then take away the triangle. So I'll do area of sector minus area of the triangle. The sector is 60 over 360, because the central angle and the arc are the same, times pi and 5 squared. You get 4.16 repeating pi. 6 is repeating there. Now the area of the triangle, since these are both 5, and it's 60 there, we saw one like this in class where it becomes equilateral. Because this is isosceles, making these the same. And if this one's 60, there's 120 left between these two. They have to be congruent, isosceles triangle theorem. So we divide by 2, and they're also 60. So it's equilateral, making this 5. So the area of the triangle is 1/2 base times height, where the base is 5. And then the height is going to be, I can use 30, 60, 90. A different color. So this is 2.5. That didn't work out very well. This is 2.5, half of 5, or in the 30, 60, 90, it's 2x, x radical 3. So it's double was the 5, half of that is 2.5. So this is 2.5 radical 3. Half of 5 times 2.5 is 6.25, and I kept the radical 3. I mean, you could already do it and get a decimal. I say round to the nearest time. So, anyways, I do this minus this. I get about 2.3. Number 10. We've got this is a nice one. The figure shows a circle with center P. Inscribed isosceles triangle. All right, so this is isosceles. Again, isosceles triangle theorem would say A is congruent to C. That's nice. I'm not actually going to use that when I solve this, but good to know. If AC, though, right here, has the same length as the radius of the circle, find the measure of ABC. So find this angle measure. Well, ABC is going to be, it's inscribed. It's going to be half of arc AC. Now watch this. They didn't give this to you for no reason. And by the way, I would encourage you, if you haven't gotten this one, think about it. Try this out for a minute. After I say this, to try it out. They say it's the same as a radius. Well, there is no radius drawn in here. How about we draw in a radius that would help? Perhaps 2 radii that would help. So think about that. I'd pause the video if you could try that. Here's what's going to be. If I draw in this radius down to A, this radius down to C, well, we just said that AC and these radii are all congruent, so I make an equilateral triangle. And if it's equilateral, they're all 60 for the angle measures. So that central angle is 60. The arc is the same measure, also 60. And therefore, our angle is half of 60, which is 30. That angle we wanted. It's a fun one. 11. In circle O, points A, B, C, and D are on the circle. Now, AD, the arc, is congruent to arc BC. And the measure of AB is twice the measure of BC. Now here's what I did. I threw in some random numbers. So I chose one of them and for the second part, where it said the measure of AB is twice the measure of BC. Well, based on what it looked like, I tried to draw it a little bit to scale. I chose this one as 120. Again, that's a random number. It was my key. I just said random number. So that's AB. The measure of AB is twice BC. Well, that means this is 60 then, right? If AB is twice, BC is half. BC is the same as AD though. So AD is 60. Because that's all it took. So again, sometimes choosing a number can help. We see that a lot in our next unit. Choose a number and see, based on that, go from there and see if it works itself out. So now we fill this in. The measure of ACD, this one right here, it's inscribed angle. Well, ACD would be half of 60 based on what I have, so 30. Is blank the measure of ADC? ADC is there. Now be careful, it's inscribed for all of this. It goes to all of that. It's half of 180, the 120 and the 60. So it's 90. And therefore the answer is a third. I'm sure there's a way to do it just with variables or just without even numbers, just thinking about it. I suggest throwing a number. Yeah, if I want to see it's 30. Part B, ADC, we just had that one, right? It's 90. And then the measure of BCD. BCD is an inscribed angle for that 180. So it's half of 180, and so it's 90. So equal. Equals. Let's finish on page 3. This actually kind of similar to a little bit of 10, some of 11. It's comparing central and inscribed angles here. It's a good one. What is the measure of angle PTR? This one. Well, we have, here, they even say, there's PS and RS are tangent. So they tell us directly. Well, this is a radius, PT, therefore this is a right angle. Same over here. That's tangent, radius, right angle. And so in the quadrilateral, we can subtract from 360. Subtract 90, subtract 90, subtract 44. And we're going to get 136. And so that's the answer for part A. Oh, I should say, yeah, that's the angle. We'll also, I can put it as the arc in a second. That's what they want, the angle. So then what is the measure of angle PQR? Well, PQR is inscribed for that arc. So it's half of this arc, and the central angle and the arc are the same. So it's half of 136, which is 68. And some of these is just identifying central versus inscribed versus random angle in or outside the circle. Let's go to the last page. Equations of circles. My apologies on yours, unless I've updated it by now. I didn't have a number there. So it's supposed to say x minus 2 squared plus y minus 1 squared equals 10. Determine if 2, negative 1 lies in, on, or outside the circle. Show your work. Now, you can verify this on Desmos. Put this in, and then put this point in. Look and see, is it in, on, or outside? Show your work, though, you got to plug these values in. This is an x and a y. So you put in 2 there, negative 1 here, and work it out. 2 minus 2 is going to be 0 squared, plus negative 1 minus 1 is negative 2 squared. And a question mark, we don't know yet. 0 squared is 0, negative 2 squared is positive 4. So we're going to get 4 and 10. They're not equal. 4 is less than 10. Therefore, the answer is in. If we would have gotten 10, it would be on the circle. If we got a number greater than 10, it would have been outside the circle. 14. That's a good one. Circle has a radius of 12. Find the number of congruent sectors you've got to break up the circle into and to create one sector area of 24 pi. So, what we should be led to is they say sector area. Excuse me. Okay, so area of a sector, that formula, I'm writing that down. The arc, measure the arc, or the central angle over 360, times pi r squared. Let's see, they give us the area of a single sector. So let's plug that in here, 24 pi. They give us the radius. Now, they don't give us the arc. So I'm going to call that x. Then I'm going to fill in the radius as 12. There we go. It becomes just like on the front side number 5, where we were working backwards from an arc length question. So watch this. I can solve for the arc. And we'll see why that's going to be very helpful. Cancel the pi. Different ways to solve this, but I'm multiplying by 360. Left side becomes 8640. That's an 8. The left side. The right side, I have 12 squared, 144, and then an x left over. We divide by 144, and we get 60. So what that says is one of our sectors must have an arc and central angle of 60 degrees, based on these conditions. Therefore, to create a full circle, I'm going to multiply by 6 because the full circle is 360 degrees. Okay, will get us to 360. So I am taking, and that's the answer, the number of congruent sectors, just to get to 360. Really, 360 divided by 60 is what we're doing. And so we get 6 sectors. There's a couple more equations to finish up. This one is just filling it in directly. So you got to know how, you won't have the equation itself. I guess you could use maybe another one on here, but just got to know the basic form. X minus this is HK, the center. Be careful too. Don't do that if it doesn't say it's a center. If it's just a random point in the circle, you can't fill it in like that. Plus y minus a negative 8 becomes plus 8 squared. equals the radius squared, r squared. So I need to divide this by 2 to get the radius. When you square that, we get 42.25. So I got a little off there. Now in part B, I can start to set it up the same. X minus 2 squared plus y plus 1 squared. I'm going to write equals r squared. I don't have a diameter or a radius. I do have a point though, and this is an xy. It's a point on the circle, xy. So I can put 5 in here, 3 in here, and work it out. 5 minus 2 will be 3 squared, 9. 3 plus 1 is 4 squared, 16. And so we get 25. You can't get the radius, but the equation, number 15, write the equation, is needing r squared. So here's the final equation. Don't forget to write it. X minus 2 squared. Again, the x's and y's are back in there. The final equation, you need those in, not numbers. Okay, plus y plus 1 squared. And then equals 25. One last change on C. Think of it as a diameter. Oh, I know. I also wanted to say on B. You could have, this is on B, plotted 2, negative 1, and then 5, 3. Okay, so the circle's going around like this. And found the radius by doing Pythagorean theorem. Count it. You would have gotten 3 one direction, how much? 3 and 4. And done Pythagorean theorem and gotten 25 for r squared. 5 for r, 25 for r squared. Alright, so it would have been the same thing. You could draw it like that, that's fine. I think it's easier just to plug in a value, but it's up to you. This one, they give us less information. They give us a diameter. So we know the diameter has these endpoints, negative 2, 6, okay, drawing not to scale, and 8, 4. Well, we always need a center and a radius. So to find the center, you do a midpoint. Just going to put in midpoint. Option 1, make a triangle, count down and over, and then count down and over half as far. Okay, I think that's the surefire way to do it. If not, you can do the midpoint formula, which is x1 plus x2 divided by 2, y1 plus y2 divided by 2. Add the x's, not subtract, add. 6 over 2 here is 3. 10 over 2 here is 5. That's the center HK. And now it becomes just like 3. 3, sorry. X minus 3 squared. Plus y minus 5 squared equals r squared. It becomes just like part B. Make a drawing, do Pythagorean theorem just with the radius, not the full diameter. Or I like to just plug in a point. I'm going to plug in 8 and 4 there. I chose Q. You choose either one, doesn't matter. 8 minus 3 is 5, 5 squared 25. 4 minus 5, negative 1, negative 1 squared is 1. These are always positive too, never negative because you're squaring them. So you get 26. I've write my final equation, x minus 3 squared plus y minus 5 squared equals 26. Okay, one last one, complete the square. This is not in standard form. All of these so far, you could at least use Desmos to verify if you choose to bring a tablet or a Chromebook to use Desmos on. 16, you notice, has a variable in it. Again, I would highly recommend you try all these. This is a good one to try first. Looks a little hard, but after doing complete the square, you'll get it. So B is just a number, and there's the equation, sort of not in standard form. They don't tell you to complete the square, but that's what you got to do. I group the x's. X squared is at that's a minus. X squared minus 4x, I leave a blank or a box. I group the y's, plus y squared plus 2y, I leave a box, equals b. And then I leave 2 boxes. Let me make this one green, first one. Okay, so then complete the square. You take the b value for each x and y, negative 4, half that, and square it. Negative 4. It's just the number that works, the process that works to get a factorable trinomial. Perfect square trinomial. Over here it's 2. Half of 2 is 1. 1 squared is 1. We factor this, it's going to be x minus 2, x minus 2. Two numbers that multiply get 4, adding to negative 4. Also going to be the same as this number before you square it. Here it's y plus 1, so it's y plus 1 squared. And here it's b plus 5. Now, part A, determine the y-coordinate of the center. That's why we did this. I'm sorry, I should have done that first. The y-coordinate is negative 1. Don't do all that work and then actually put positive 1. It always looks like the opposite number here. The center is really 2, negative 1. So be very careful. You do all the right work, and then they ask you just something slightly different that could throw you off. So negative 1 on that one. Part B, the radius of the circle is 7. What is the value of B? You can actually find it. Now, here's another one where they want to try and kind of trick you into doing this. Some students will say b plus 5 is equal to 7. So then b is 2. Well, your equation, you made this be r. But really, I mean, look up here what we did. That side of the equation is r squared. Okay? So, b plus 5 is actually equal to r squared. So we need to square the 7. Let's get rid of that. So we need to do 7 squared. So okay, r is 7. Square it, r squared is 49. So that's what goes here. Subtract 5. So b is 44. Last one, it's a parts one. And this is using the center of a circle by a perpendicular bisector. So this is coming from the center, it's perpendicular, therefore it's bisecting this chord. So this is x as well. And then it becomes a parts one. Now, one part is x times x. Then the green is 2 times this one. And since this is 5 and this is a radius, we can conclude this is 3. Therefore, it's 8 for the second part we need. So we get x squared equals 16, square root, we get 4. Make sure to study the formulas, degrees to radians, the process, we look at a diagram, which one to do. Also, we did 3 proofs. Review the 3. We did inscribed angle theorem, how to show that. We did what I call party hat theorem. An exterior point, you have 2 tangents, they're congruent. And then we did, inscribed angle theorem corollary 1. 2 inscribed angles that go to the same arc are congruent. And then inscribed angle theorem corollary 3. Opposite angles of an inscribed quadrilateral are supplementary.